Okay, thank you. Hello, everyone. So we are getting started, so please take a seat. We are starting in a few minutes. Well, we can all start with a vibrant and warm cheering for our great host. Please, thank you. I'm very, very, very happy and honored to be here with you. And thank you for being here today with us. It's a special occasion for University of Milano Bicocca. It's a special day indeed, which we want to start with a compelling conversation with Professor Giovanna Iannantuoni, Rector of University of Milano Bicocca, and our renowned host, Professor Carlo Frank, Ogden Professor of Fundamental Physics at Durham University. So thank you again. We are here to celebrate astrophysics and science, and it's a very special event for University of Milano Bicocca. What's the relevance of this day for Bicocca community?
Well, first of all, I think that maybe I should do something.
First of all, the mic. And okay.
It works.
Okay.
Okay, no. Speak. I speak, this is not my problem, to speak is not my problem. Okay. So today is really a special occasion. I thank a lot Carlos to be here with us to celebrate astrophysics and in general science, and also to celebrate University of Milan Bicocca, if I can say this. And for me, first of all, it's very special to be in presence, to have some senior member, and thank you, Professor Sironi, to be here, and many young students. Because the heritage of science is a very important point of this process. So in the understanding that science is a process, that is a long way to do some discover, that you need to study, to work, to believe in this. And so this is a research day, but in the new meaning that I think science is also something open to the society and to citizens. So I think that as a public university, we have this responsibility. When we have a very top scholar group, as my astrophysics are, we need to open up our research and our vision to the society, to the citizens, to the youngest, in order to improve the level, the cultural level of the society. But we speak later about this. So this is a very special day. So thank you. Carlos.
Yes, is my microphone working?
Yeah.
Good. No? Somebody said no.
We give them.
I don't know if he...
Okay, 1, 2, 3. Okay. Okay. Yes. Now it is working. Yeah. So, well, first of all, I would like to thank the rector and thank Michele Fumagalli and his colleagues in astrophysics for the tremendous hospitality that I have enjoyed. I've only been here since yesterday, and I'll make a confession. I've always loved Italy, not just because of the football team, but for many, many reasons. And Milano in particular is a place that I've been to many times before. And I now have a new reason to come to Milano regularly, which is to visit my colleagues in the astrophysics group here, which has grown enormously just in a few years and has become not just one of the main centers for astrophysics research in Italy, but indeed in Europe and in the whole world. So it's wonderful to see, particularly since some of the people in the astrophysics department came from my university. So for me, it's a source of pride that we trained at least two of them that I can see here, Alejandro Benitez and Michele Fumagalli. So it's thank you very much for your hospitality, and of course for the hospitality of the rector. I already had a very interesting conversation with you this morning, and it really is wonderful to be here.
Thank you.
Thank you. I will speak very loud because I'm used to it, because it's not working, but no problem for me. So again, a little more. What inspired you to follow this kind of career in science?
Well, how long have we got? So my path for science wasn't straightforward. Like all children, I was curious about everything. And I come from a family, my mother was a professional pianist. My father was a doctor. My mother wanted me to be an artist. My father wanted me to be a scientist. I didn't know what to do. I wanted to do everything that was possible. But eventually, I had one event, which was like an epiphany. I had started on the wrong track. I had started on the wrong track for me, not the wrong track in absolute sense. I went to engineering because my mother said to me, if you're a physicist, you're not going to be able to earn your living, so you should go to engineering. So I went to engineering, and I enjoyed it. But after the first year, I had an epiphany. I went hiking. I was born in Mexico, and I grew up in Mexico. And I went hiking in the south, in some lakes, and the temperature was Milano-like temperature. It was too hot to sleep in a tent. So I put my sleeping bag outdoors. Then in the middle of the night, I woke up. And I saw the most incredible thing that I've ever seen in my life. The Milky Way, the stars. It was a perfectly clear night. You could almost touch the stars. You could almost try to see whether they were solid or gaseous. And it was just an amazing thing. And at that point, I decided, I want to understand where this comes from. I want to understand why is the universe like this? I want to understand why are we here? And so I went back to Mexico City, and I told my teachers, I'm quitting engineering. My dad then said to me, good, I offered to support you only until you're 60. And when I turned 60, he called me up and said, good, I don't have to do that anymore. And then I never looked back. It was one of the happiest days of my life when I decided that my vocation was really science, and that the curiosity as I had as a child could be put into practice by trying to understand the universe around us.
Thank you. Thank you very much for your inspiring words. Professor Iannantuoni, Rector Iannantuoni, we are approaching, Bicocca is approaching its 25th anniversary, of course, and the strong belief, which I find very fascinating, is that culture and science are the main engines that drive innovation. So echoing the title of this conversation, why science is a key element in our society?
So now I will use my background as an economist also to answer to this question. We are in a very special time, no? Because we are in the post-COVID period, and we have many problems, right? There is the war, there are many inequalities in our countries, in income, but especially what is really worrying me is the inequality about level of education. Inequality about level of education that is growing, and the gender gap, the inequality that young women risk to have. So, if you look at Italy, these are data that are very similar around Europe, but in Italy are a little bit worse. You have that our level of participation, of work participation, active participation to the market is very low, and especially for women, and especially in the so-called STEM science. And so this is a really huge problem, because we risk in the future to have big problems, because if we don't teach to our young people, to our children, that culture and studying gives them independence and capability to understand the world where they live in, then we are really, there is no star, no research, no Nobel Prize that is enough for this loss. So I think that we have really to take this responsibility and seriously work about this. So, as economists, we know that the growth depends from two dimensions. One is the so-called human capital, and these young people studying in my university, so we are doing a very good job because they are great, okay? And the second engine of growth is technology, innovation, good innovation. And innovation comes from research. So if we do good research, then we'll do good innovation. And from human capital and good innovation, then we'll improve the welfare and the life of our children, we leave this heritage after us. And I believe very strongly about this.
and next citizens of the universe.
Absolutely.
So,
also, alien planets will take care also about their inequalities.
Professor Frank, you have been devoting a lifetime career to science, particularly the nature of our universe, dealing with the most complex, can I say, questions of the human beings. What's the relevance for pure academic science in our society, as you said before?
Well, the rector just explained some of it beautifully, and I just want to add a couple of thoughts to what she said. So I am an astrophysicist, a cosmology, so I spent all the hours of the day thinking about dark matter, dark energy, the origin of the universe, galaxies. So these are really abstract questions. This is a basic science at its most basic. So everybody's entitled to ask, why should I get a salary? Why should society invest resources in something as abstract and seemingly pointless as the subjects that I study? So let me try to answer that, just supplementing what the rector just told us. So first of all, we study abstract science, we study astronomy, first of all because we're curious, and curiosity lies at the root of our success as a species. But that's only one part. The other part is that the technology and the innovation on which our modern lives depend, every single development there can be directly traced back to a discovery made by basic scientists trying to understand the fundamental principles of nature. So for example, and these, of course, discoveries are unpredictable. So nobody could have dreamt that Lawrence Bragg, when he was trying to understand the nature of light, would discover X-ray diffraction, which then 30 years later led to the discovery of the double helix and to genetics. Nobody would imagine that John Bardeen, who was studying the quantum properties of solids, would end up laying the foundations for the discovery of the transistor, which is the basic unit on which all our electronic devices, telephones, computers are based. Sir Tim Berners-Lee, as he is now, he was a particle physicist at CERN, and he was very worried that he didn't know where seminars were happening. And so in order to try to solve that problem, he invented what became known as the World Wide Web. So an effort to improve communications in CERN led to the biggest industrial, economic, and social revolution that we have seen through our lives. And more recently, geneticists who were interested in just trying to understand the basics of life, their discoveries led directly to the vaccines against COVID, without which our societies would have collapsed. So that is the history of science, is that behind every innovation, behind every technology, there is always a direct route to research in the basics of trying to understand the world around us. So that's why investing in pure science is about the best possible way in which a university or a government can put their resources. That's why I wake up in the morning and I don't feel guilty when I get a paycheck at the end of the month.
Right, thank you. Also, we can also make it in parallel to humanities with Lorenzo Valla, which was a great Italian and studying philology in the 15th century. I think he discovered that donation of Constantino was a fake one. So everything can lead to something else. And we fortunately see marked rise of interest of the young generations in STEM disciplines. And we can think about, for example, the national plan to innovate the education system, empowering the students with the tools needed for succeeding in a growing digital era we live in. Which role do universities have in sparking this interest in STEM discipline?
Well, the role of university is a leading role about this. So again, we have to take responsibility. I like this word, so I speak about responsibility very often because it's easier to not take responsibility. Instead, we have the responsibility to open up our doors and to communicate as a dialogue with the society. And so this is what we should do, and we should do this from very early stage education level of the students, so we don't have to wait that they choose university before explaining a young girl or a young boy what a scientific experiment is. So we have to teach the teachers at also elementary level, even before, to understand what is science. And this is the best way to have higher number of young people getting passion for science. Because if you don't meet ever that sky, Carlos, that you were talking about, so if you don't do that experiment, if you don't do that, maybe you will never ever become one of the best cosmology that we have. So we need, to give the chance to young people to have that kind of passion. Everybody of us that is an academic, we become an academic because we have the passion for research in every field that we study. And as Milano Bicocca is a very interdisciplinary university, so we have many different fields, from psychology to medicine, from economics to statistics, mathematics. We have many different fields. And I think that what is also very interesting for my students is that when they come to Milano Bicocca, they can talk about physics, but they can talk also about psychology, they can talk about economics with their fellows and also with seniors. So I like very much this very Rinascimental view of science, where there are no borders. When I was in Cambridge before, we were talking about that. What is my memory? The best part, where the dinner or the college life, where you talk about with people from many different fields, and if you are curious, then you learn many things, and also you are capable to respect, to know every field and every research and every discover, from the poetry, the new poetry, or a new interpretation of an old manufacture, to cosmology. So be curious. The young people need to be curious. If they are not curious, then we have a problem. But in order to get people to be curious, we need to show them things. We need to talk to them. So for this reason, for example, we have a 0-6 years program. So we have a kindergarten structure for our littles, but also for the externals, where we do many STEAM try in order to really get the passion of science from a very early stage of their life. And I think that this is really the bet that we have to win.
Thank you very much. And finally, I can relax a little bit with the mic. Professor Frank, you want to add something?
Well, just to add another footnote to what the rector has just expressed, again, beautifully and clearly, and that is the fact that human knowledge has no boundaries. Just like science has no geographic boundaries, it should not have any. Likewise, intellectual activity has no boundaries. And we all know that the world today faces some truly existential problems that we all know about, climate change and the loss of biodiversity, food, water, energy scarcity, and aging population. And we all have a role to play in trying to confront those challenges. Of course, scientists are at the heart of confronting those challenges, but scientists alone are not going to do it without economists, without sociologists, without philosophers. So it has to be, I'm really worried about the future of mankind, I should confess, because I've been thinking about it lately, and maybe I'm influenced by a person that both the rector and I know very well. She was at Trinity College in Cambridge, and some of my colleagues here know, who's now a Lord, Martin Rees, the Astronomer Royal, who is an astronomer, but he thinks very deeply about this existential crisis. And maybe both of us have been influenced in thinking that we do face serious problems, and the solution won't come from one discipline. The solution will come from a concerted effort across fields of knowledge and across not just of knowledge, but also all sorts of fields of human endeavor, engineering and technology, computing. Everybody has a role to play. And I think we should take these things much more seriously than I think we're taking them. The only ones I'm not very confident about are the politicians. But although in Italy, at least you're doing reasonably well, much better than we're doing in my own country, the United Kingdom.
Thank you very much. I totally agree. A cross-fertilization, a fertile hug of different disciplines is the cultural solutions. And is this the reason why you boast several collaborations with also philanthropic organizations? For instance, the Ogden Trust, which is a foundation that enhances the physics education and engagement for all new people. Why do you spend so much effort and time in these activities?
Well, so the question is, so I've been very lucky in my university that I have come across philanthropists who have made very, very large donations and to the university, as a result of which we have a number of wonderful buildings that were paid by donations. And the rector is also told us at the beginning the importance of having connections to the outside world. Now, philanthropy is quite an interesting aspect of support for science, because the philanthropists that I know, the first thing they tell me is, if you want some money from me, I'm not going to give you money to do what the government should do or what the university should do. I'm going to give you money to do things that neither the government nor the university would do. So philanthropy plays that role, not trying to fill in the holes and the gaps that should be filled by the state or by the university, but trying to do new things that wouldn't otherwise happen. So in my own university, we have this wonderful building that was designed by a top architect, Daniel Libeskind, and that would have never happened. The university would have never, in the wildest dream, contracted one of the top architects in the world, but philanthropists had enough resources to do so. So you have to be careful with philanthropy, I should add, because you have to do due diligence. There are lots of rich people around, and they've now become very popular, all the oligarchs and all the people whose yachts have been confiscated. Some of them like to give money to science just to become respectable and to gain a place in society. So you have to be very careful to investigate the sources of the money that you are going to accept as a donation. So there are legitimate and ethical ways of making lots of money in a capitalist society, and that's fine. If we can benefit in science from that, that's good. But don't, I've learned not to accept donations just because somebody wants to give you money. Some people don't do it for the right reasons, but most of them do. All the philanthropists that are, as far as I know, that have made contributions to my institution, they're all very, very genuine and very interesting and very pleasant people.
Yeah, about philanthropy, you know, in Italy we have very few philanthropists for many reasons, also fiscal reasons. So yes. In Anglo-Saxon worlds, of course, philanthropy is very, you know, it's more common because you have fiscal advantage from that. Well, we have to say this, no? So you take advantage from philanthropy. And in Italy, we don't have that. As a university, we are the first university to start this crowdfunding for young researchers. So we, every year, we launch 4 or 5 ideas that are very strong from only, I want just young persons. They take care about it. And as a rector, I double what they have from crowdfunding. So very small donation, even €100, €200, but we always get the point that we ask in this crowdfunding. And then I double the money so they can do some research in a more also, you know, open way. So this is another way of thinking. Of course, we never reach that kind of money that you got, but you know, it's a signal.
Yeah, I mean, you're also a young university, so you have to wait a little bit until some of your graduates
I'm not patient. So.
No, well, true. Yes, they become successful industrialists and they want to give something back. Because, you know, philanthropists don't just give you money for no reason. They always want to give something back. And so alumni are a very important source of philanthropy.
I agree.
Yes. So no, it is true. I was aware that in Italy it's not the same as in
No, because it's just, you know, even you pay taxes on what you give. So, you know, it's really crazy to be crazy.
So we can say be curious, but cautious about the origin and the nature of the universe, but also of the donations and funds.
Absolutely, yes.
Okay, so again, beside STM disciplines, we also see a shift to new teaching methods, as also recommended by the European Commission. Bicocca is investing in cutting-edge new methods. We can quote, for example, the Vivaio Bicocca, the open-air laboratory for interactive teaching, and, of course, the brand new 40 centimeters telescope we are inaugurating today, and maybe make an applause for this. Which I think it's a great thing, because I'm Milanese, and it's the first free public observatory for the Milanese city, so I'm very happy. So the question is, why these methods are so important, and why Bicocca is investing so much in the spaces, in the new spaces where teaching moves away from its traditional educational path?
So first, just a very short comment about this telescope that we're gonna see. We see what the skies look like tonight. So my dream is that 4 years girl, maybe from a family that is not full of physicians or scientists, can come to Bicocca, can see the sky, and maybe when she will be 40, she will be a Nobel Prize in cosmology. So this is the hope, right? That we give an occasion to people to have a passion, to build a passion. From the other, for your question, so, you know, we have very new building because we are a very growing university. So 24 years ago, we had 3,000 students. Now we reach almost 40,000 students. We have multidisciplinary. We are growing in many dimensions, financially, grants, you know, every dimension that you can imagine, we are growing. But I think that we cannot allow our students to study as my parents or my grandparents studied at university, you know, with the standard, you know, podium, and then the teacher speaks and the students listen, because this is a very old way to teach and to learn. So when I was teaching, because as a rector I don't teach now anymore, I was, when I came back to Italy, I was, you know, used to walk around the room, ask questions to students, and they were really worried, not because I am a scaring person, I hope, but because they were not used, you know, to an interactive method of learning. And instead, we need to have your attention. So we need to have the attention of the students, because this is an occasion for you to grow as a person, to learn astrophysics, to learn cosmology, but also to learn who you are as a person, to engage in a challenging conversation with your mentor, and also with your fellows, with the other students that do other things. So I think that is very crucial to open up our mentality, our head, our brain, and to learn other methods of teaching. So I'm going to change our campus a lot. Maybe you know about this. You don't know, Carlos, but I know, because we are spending a lot of money. We have a really big budget. So my general director, no, he's here because he's the money guy. So, and because my vision is that our campus is a laboratory where my scientists should make their research, first of all, in our campus. So my scientists of material, new way for, you know, the energy. So we have many, so of course the green change, but also the digitalization. So we are, you know, having much more green after a while, but this will be a new kind of green. So very technological. We are doing many extraordinary things. And I want that my students are involved in these things, so they can do their thesis or their study, also about participating to the research that really happens in Milano Bicocca. So I hope that I will leave to my, you know, successors a campus that he or she will not recognize. Everything will be, we don't have to be scared about changing. I'm not scared about changing. So.
Never be. Thank you very much. And of course, Bicocca and Milan is very happy to host now the new telescope, which proudly stands on the U9 Koine building. And I really like this thing because koine, you know, was the Greek ancient word describing the common language without differences and idiosyncrasies. As well, the observation of the universe shows us we are all brothers and sisters belonging to one race, the human race. And so I'm very, very happy. And for safety reasons, of course, we cannot bring you to the site at the moment. So we made up a very short video clip to present the telescope.
We're here in front of our new telescope. It just arrived on campus. We are very excited to start working with it to strengthen the core missions of our university, which are outstanding teaching and communicating science to the public. And we want to do this with a tool that is a professional telescope, so that both students and the public can not just only enjoy the view of the sky, but can also learn about the scientific process and what science and technology is about. The telescope will bring new emphasis to the activities of our international master degrees and new innovative teaching activities that the university is pursuing. We will transition from traditional teaching methods to project-oriented ones, where the students have the opportunity to develop their own science question, collect the data with the telescope to address those questions, and then analyze the data in a way similar to our traditional research is done.
This wonderful instrument is a completely robotic telescope which can be operated from remote, for instance from our own offices. It's a 40 centimeter telescope with optical configuration reaching at the end. The two instruments which equip this telescope are a photometric camera and a spectrograph. In parallel to the telescope, there is a small solar telescope which let us to use the telescope also during daylight to observe sunspots and protuberances.
This initiative is conducted in a very dynamic environment like our astrophysical unit is, where there is a strong synergy between teaching and research. So research like me can teach the young student how to look at the sky. This experience won't be open just to our students in our Bicocca, but in fact will be devoted to younger students at different schools and also to the general population of Milan, that will have a taste of how the sky looks like.
The telescope is operated at the astrophysical unit of Milan Bicocca, where we do research from the biggest structure in the universe to galaxy formation and to the small structures such as black holes. And this research attracts researchers from all around the world, which makes Milan Bicocca a really international base to study and to work.
Very, very nice. So thank you again, Rector Ian Antoni and Professor Carlos Frank, for sharing your vision about science in society. This telescope is very wonderful, very important, because I hope and I think that around it will be also built a new learning experience for teachers and for students, of course, and also a new method to communicate with the society, not only the academic one, of course. Before going to the public lecture, unprecedented public lecture by Professor Frank, I want to deeply thank Rector Ian Antoni, because she strived so much, so vividly she wanted the new telescope to be part of the campus, and of course Professor Michele Fumagalli and Professor Mario Zannoni in alphabetic order, and Dr. of course, and Dr. Matteo Fossati, who worked on the technical design, and also to make this dream come true about the telescope, which is, I repeat it because it's very important, a great thing, a great an enhancement for the Milanese society. I'm very happy about that. And of course, thank you to the support office, which helped them a lot. So now, I'm very, very honored and excited to introduce the unprecedented public lecture from Professor Carlos Frank called How Our Universe Was Made, All from Nothing, a great and compelling journey from the very first seconds after Big Bang through the wellspring of galaxies towards the so-called dark energy. We and you are so privileged to be here live in presence, hearing from his live voice, as Professor Frank is one of the most important cosmologists, astrophysics, and physicians of the world. As mentioned before, he's Ogden Professor of Fundamental Physics at Durham University, won the gold medal in 2014 of the Royal Academic Society, and furthermore, is a fellow of the Royal Society and member of the Royal Society Council, and also director of the Institute of Computational Cosmology. So please, again, make a warm and vibrant cheering for Professor Frank.
Thank you very much, and thank you, Giovanna. That was very interesting. And as she walks, I'll make a confession. In the car, she told me something. I'm not sure she wants me to repeat that, but she said to me that she's a revolutionary. And I think you're very lucky to have such a revolutionary and innovative and visionary rector in this university. Very good. So now I'm going to tell you, leave this world behind and tell you about the universe as a whole. And the title of this lecture is How Our Universe Was Made, and all from nothing. By the way, I talked about the building by Libeskind. This is the building. I need to switch this on, I think. Otherwise, it doesn't work. Right. So this is the building that I referred to, and here's where the Institute for Computational Cosmology resides. Now, so the title of this lecture may be a little bit strange. All from nothing. All is clear. All means the universe. Nothing will become clear later on. So this is a lecture about cosmology, and cosmology is the branch of science that asks some of the most basic questions that humans can ask, questions such as how did the universe begin? What is it made of? How did it evolve to its present state? And what does the future hold? So these are really basic questions that were not the first to ask. In fact, they have a long history in the history of civilization. And I would even go as far as saying that human civilization began where our ancestors started asking these sort of questions. And of course, physicists are not the only people who study these issues, and these are questions that interest not just physicists, theologians, philosophers, artists, many different disciplines try to answer these questions in different ways. But what's special, or if you like, unique about physics is that we have a very, very well-defined and in rigorous methodology based on the laws of physics. Now, the laws of physics are general rules about natural phenomena, and we're familiar with many of those. Newton's law of gravitation, for example. So these are invariably, actually with one exception, laws that are discovered empirically in the laboratory. The exception is the theory of general relativity, which, as far as I know, came out of Einstein's brain rather than experimental activity, as all the other laws of physics come from. So these are laws that are discovered in the laboratory, and then they're expressed mathematically, which allows us to manipulate these laws and learn new things about our universe. Now, so all these laws of physics that we're going to use to understand the universe are experimentally verified on Earth. And to me, one of the greatest mysteries of our universe is why is it that the laws of physics that we discovered in the laboratory on Earth seem to apply not just on Earth, but everywhere in the universe, at all places and at all times, in conditions that have no resemblance to those that we have in our laboratories. The Big Bang, for example, the conditions that were completely different, and yet the same laws of physics that operate on Earth operate, as far as we can tell, and I'll give you evidence for this, in those extreme conditions. So if you get one thing from this lecture to keep you awake at night, is to ask yourself, why are the laws of physics universal? Now, so the building blocks of the universe are galaxies. Galaxies are collections of stars ranging from even a few hundred to up to 100 billion stars. We live in a galaxy that is very similar to that one, and is not our galaxy. Of course, we cannot take a picture of our galaxy, but this is a twin of our galaxy, and we live about 2/3 of the way from the center of the Milky Way galaxy. Now, let me put you in the right cosmic mood by showing you a movie made from real data. It's a tour of our local universe. And I'll ask the projectionist if they can turn the lights off here so you can see this voyage around our local neighborhood. So we can see what are we talking about when we talk about the origin of the universe. So this is a movie made by colleague Brentoli in the University of Hawaii. Can we not switch the lights off?
Spegnere la luce?
Let me stop it and start again, because you really need dark for this. I mean, we can see it with the lights, but then you miss half the fun. So astronomers are people of the night. We managed to do this yesterday. If it doesn't work, I'll just sort like this. But now, if I talk on the microphone, maybe. So is it not possible to switch off the lights on the screen? Yeah, I think, right, I think if you talked on the microphone. Brilliant, thank you. Grazie, grazie. You can just leave the lights off because there's many other things that you really want to see in the dark. Okay, so let me then, I hope I get injury time from this. And so I said this is a movie made from real data. There's only one small bit of artistic impression. So here we start our journey going through the constellation of Orion that you see there, brilliant. And next to the constellation of Orion, there's a cloud of gas and dust called the Orion Nebula. And these are the places where new stars are being born. So the Milky Way galaxy is making stars at the rate of about one new star every year. This is a very famous nebula as well, for obvious reasons, called the Horsehead Nebula. Again, a place where new stars are being born. This is yet another nebula called the Carina Nebula, and this is an example of something that's very common. Stars tend to be born in collections of a few. You can see 4 or 5 stars being born there. Now, but not all these nebulae are birthplaces of stars. Some are the opposite. Some are graveyards of stars. So this is the Crab Nebula, and the Sun is going to do the same thing as the Crab Nebula is already doing. So this is a star that ran out of nuclear fuel, and when it did that, it ejected its outer layers and left behind something called a pulsar, which you can see pulsating there. Our Sun is not quite do this, but it's going to do something quite similar. Our Sun will not produce a pulsar, it will produce a different kind of star called a white dwarf. Now, this is the only bit of artistic impression where we leave our galaxy. Of course, this is not our galaxy. Similar. Galaxies are about 50,000 light years across. It means it takes 50,000 years for light to go from one end of the galaxy to another. So you can see that galactic communication is not that simple. So here's, these are neighbors of our galaxy called the Large and Small Magellanic Clouds. And now we're going to head towards nearest large neighbor called the Andromeda Galaxy, which is at about 3 million light years away. That's Andromeda, or M31, has a companion called M33. Itself has a cloud of gas and dust, where new stars are also being born. So it's about 3 million light years away. Now we're going to head eventually towards the cluster of galaxies that you see here in the corner, called the Virgo cluster of galaxies. But before that, we'll take a little detour to see some of these amazing things that nature has made. And I'm going to tell you where they come from later on. So these are grand design spirals that you see here so beautifully. This one is interacting with a companion. And how the universe made these amazing structures, we should come to later. Now, this is called the Virgo clusters of galaxies. It's a collection of about 1,000 bright galaxies, and it's the nearest big cluster to us. It's at a distance of about 3 million light years from us. Sorry, 30 million light years from us. And at the center of the Virgo cluster, there's a very famous galaxy called M87. And it's famous because at the center, it has a very big black hole that weighs about 1 billion times the mass of the sun, called a supermassive black hole. At the center here, all galaxies, including our own, have such monsters in the center, and you can see a little bit of the digestion of material around the black hole in the form of that jet. Now, so that's the universe around us, and that is what we're trying to understand. The question is, where does that come from? And I'll try to give you an answer later on. Before that, let's just ask a simple question. How many galaxies are there? Well, many. There are about 100 billion. I'm using billion in the American sense. So by billion, I mean 1,000 million. I don't know in Italy whether a billion is British. It's 1,000. Oh, good. Okay. So I should say in astronomy, there's all these large numbers and the billions and so on. Just like in the economy nowadays, but because the universe is big and we are small compared to any scale in the universe. But of course, it's not size, but complexity that makes things difficult to understand. The universe is very big, but it's actually quite simple, as we shall see. Unlike a human, who is much smaller, but a lot more complex and much more difficult to understand. So that's why I think physicists and astronomers have advanced more in the subject matter than biologists and geneticists. They deal with a far more complex system than we do. At any rate, the visible universe has about 100 billion galaxies, each with about 100 billion stars. So there are many, many stars in the universe. In spite of that, galaxies, of course, are made of stars. Stars are made of atoms, of the atoms that were familiar here on Earth, the atoms that you study in chemistry, the atoms of the periodic table. But in spite of that huge number of stars, normal matter, the matter made of normal atoms, makes up only about 5% of what the universe contains. About 25% is matter, completely different, not made of atoms, something that we call dark matter, which, as the name indicates, does not emit light at any wavelength. That makes up 25% of what the universe contains. But the lion's share of the universe is not even matter, it's something that we call dark energy. And the dark energy, which was discovered relatively recently, is a mysterious form of energy which opposes gravity, acts to oppose gravity, is a sort of anti-gravity force, and it is causing the expansion of the universe to accelerate. I'm going to tell you more about that very soon. So both the dark matter and the dark energy are still very mysterious. We think we know what the dark matter is, but we don't know for sure. And for dark energy, we know even less. In fact, we know so little that in one slide, I'm going to bring you up to date with everything the experts know. So after one slide, you'll be as expert in dark energy as the professionals who get paid to study that. So the dark energy then has to do with the expansion of the universe. The expansion of the universe was discovered by this man. Unfortunately, I like to walk, but I was told to stand here, so I need to talk to the microphone. So excuse me if I sometimes get distracted and I walk, but I'm... Oh, so if I do that... Oh, this is much better. Then, okay. Is it still on? Okay, is it on? No. No, it is. No.
You can take maybe this.
The center. Right. Hello? Okay, so this is better. I'll just wonder because I need to change my slides there. But the dark energy has to do with the expansion of the universe. That was discovered by this man, Edwin Hubble, of telescope fame, the Hubble Space Telescope, seen here at the time when people were actually allowed to smoke in their offices. And now Hubble discovered that all galaxies around us, all the galaxies that you saw in the movie, they're all moving away from us at a speed that's proportional to the distance. And he discovered the expansion of the universe. Now, of course, you might wonder, well, why are all galaxies moving away from us? Are we at the center of the universe? The answer is no. Any other observer would see exactly the same thing, would see all galaxies moving away from them. Now, so that was known almost 100 years ago, but the big surprise came at the end of the last millennium when, using distant supernovae, astronomers realized that not only is the universe expanding, but the expansion is getting faster and faster. So the expansion is accelerating. Now, that came as a big surprise because if all the universe had was matter, then matter produces gravity. The universe started with an explosion, the Big Bang. The gravity would try to bring back the universe because of a force of attraction. And yet, what we saw is that the universe is expanding faster and faster and faster and faster. So something seems to be pushing against gravity. And that is what we know as dark energy. So, and you should be suspicious when scientists invent a word like dark energy. They're just really telling you, I have no idea what I'm talking about. Let me give you a mysterious name just so that we can try to convince the funding agencies to give us money to study this phenomenon. So now, in fact, even though we don't know what the dark energy is, the discovery of the accelerated expansion of the universe was so important that it earned the Nobel Prize in Physics to 3 colleagues in 2011. So what is the cosmic dark energy? And this is the slide I promised. After that slide, as I say, you'll be up to date with current developments in this subject. So it's a form of energy that produces a repulsive force, you said, opposes gravity, and is causing the universal expansion to accelerate. Now, most of the universe is empty. You might not think so if you go to the Piazza del Duomo, but that's a very special place in the universe. You may have seen that in the movie. Galaxies are very, very far apart from one another. Most of the universe is completely empty. And in physics, we call empty space the vacuum. So whatever is pushing the galaxies almost certainly has to do with the vacuum. So it almost certainly has to do with empty space. And that's about all we know about dark energy. We know it's accelerating the expansion of the universe, and we know it must be connected somehow to the properties of empty space, to the properties of the vacuum, which is the word nothing in the title of this lecture. So now let me tell you a little bit more about dark matter. We know a lot more about dark matter. So this matter is matter that doesn't produce light at any wavelength, and so it's dark. And you might wonder, well, if we can't see it, but how on earth do we know it exists? Now, so this is where physics really shows its immense power. And in this case, the bit of physics is a very elementary part of physics. It's just Newton's laws of gravity. So Newton taught us that matter produces gravity, and gravity produces motion. And he attested that when he got hit in the head by an apple. Now, of course, this works both ways. If you measure motion, then you know the laws of gravity. You can infer how much matter there should be to produce that motion. Astronomers are very good at measuring motions, in particular the motions of stars going round and round the center of a galaxy. From that motion, using Newton's laws, they can infer how much matter there should be in order to account for the velocities of stars around the center of the galaxy. And the big surprise is that there doesn't seem to be enough matter in the form of stars and gas clouds in a galaxy to account for the large velocities of stars. So the stars are moving too fast to be, for their motions, to be explained by the gravity of the matter that we can see. So the inference is, well, there must be matter that we cannot see, and that's otherwise the stars would have all flown apart. So the reason that galaxies are structures that you can identify is because there is a sort of glue called the dark matter. I was in London the other day, walking around, thinking about this. There was a little subtlety I didn't understand. I was so lucky that I ran into Newton. So Newton's come back to life as a musician. I don't know how many of you know who this fellow is. Yeah, he's Brian May. And so it's quite interesting. Many of the young people no longer know who Brian May is, but he is a very famous musician. But he is Newton reincarnated. It's the same, the nose is the same, mouth is the same, of course the hair is the same. And so he's Newton reincarnated. And I'll tell you why he decided to become, he's got a PhD in astronomy, by the way. I don't know him because he's a celebrity. I don't hang out with celebrities, but I do hang out with astronomers. So he is a professional, but not a professor. He has a PhD in astronomy. So I will tell you later why he reincarnated as a musician. Now, so the picture you should have of a galaxy is a little splash of light embedded in a big clump of material that we cannot see, that astronomers call a dark matter halo. So that's very direct evidence for the existence of dark matter, but there's even more spectacular evidence for the existence of dark matter, and that can be illustrated with this wonderful image from the Hubble Space Telescope. Here's a galaxy cluster. We saw the Virgo cluster earlier, and you can see normal galaxies like those, but as well as those, you can see these very strange features, arc-like features. These are called arcs, gravitational arcs. Now, these are also galaxies, but there are galaxies that are a long way behind, what did I do with my microphone? They're a long way behind the galaxy cluster, and the light has been deflected by the gravity of the mass in the galaxy cluster, because what Einstein told us is E equals mc squared. It means that mass is related to energy, which is light. So mass interacts with light, and in fact, it deflects the light from these distant galaxies. And if you deflect the light from an image, the image gets distorted in this characteristic arc-like pattern. So these are galaxies whose image has been distorted by the gravity of the cluster through which they are passing. Now, so Einstein knew all about this, and he wrote a letter to his colleagues explaining how, in this case, a star would be a galaxy cluster, deflects light, and if light is deflected, then the images are distorted. So let's do an experiment here, showing you, here's a picture of something called the Hubble Deep Field. This is the deepest image humans have made of the universe. So these galaxies are so distant that the light has taken most of the age of the universe to get to us. I'm just going to use this as background, as a sort of tapestry. And the experiment we're going to do is that we're going to grow a lump of mass, of dark matter, here gradually in the computer, just by solving the equations of relativity, and we'll see what that growing lump of mass does to the images of the background galaxies. So here is a lump of dark matter growing. As it gets more and more massive, it's now like a galaxy cluster. You can see that it distorts the light of this background, producing exactly that characteristic gravitational lensing, as it's called, pattern. Now we can use the elongation of these arcs to tell us how much matter there should be. And the result is the same as with the galaxies. There has to be approximately 10 times more invisible, 6 times exactly, but approximately 10 times more dark matter than the matter that we can see in the images. So that is clear-cut evidence that most of the mass in the universe is actually dark matter. So that's what I just told you. So what is the dark matter? Well, this is a very important question. We don't know for sure yet, but we have quite a good idea of what it probably is. Here's a picture of the Big Bang that I'm going to show you many times. Here's the Big Bang. We know the universe is 13.7 billion years. So this is all the early phases of the Big Bang. This picture, of course, was made by particle physicists. I don't know why they have so much time to make pictures like this. So they compress all the time scales. So all the first few 100 million years when particle physics is important is most of the diagram. And then they let astronomers and biologists just appear here at the end of the diagram. But the universe is about 13.7 billion years old. And when it was very young, about 10 to the minus 10 seconds, so it's a decimal point 9 zeros and a 1 of a second, that's when the dark matter probably came into existence as a form of elementary particle distinct from the protons and the electrons and the neutrons that make normal matter. The best candidate for dark matter is something called dark matter. Now, but of course, I'm going to show you lots of evidence, indirect evidence, which I show you some pretty direct, but I'm going to show you some indirect evidence that the dark matter is an elementary particle. But of course, ultimately, we want to discover these particles. So if these ideas are correct, this room is full of cold dark matter particles, but they don't interact with anything. They go through our bodies and they just don't do any harm, which is good for our health, but it's very bad if you want to detect them because they go through the detector and they don't interact with it, but they don't detect anything. So, but there's a big search for dark matter, and some by Italian physicists working in a laboratory in the Alps. And I don't know if you've ever seen an experimental physicist, and if you haven't, this is what they look like. And there are several of them currently trying to find out what the dark matter is. So these experiments looking for dark matter take place normally in deep mines. Here's an example of those, in order to shield the instruments from all sorts of debris that drains onto the Milky Way, onto the Earth from outer space. So the experiments are not in the most hospitable laboratories, but it's an example of one. There's activity going on, say, not in Italy itself, but the Italian scientists are very, very prominent in many of these experiments. In fact, the principal investigator, one of the main ones, is a colleague of mine, an Italian woman, actually, who is extremely impressive. And she might be the Nobel Prize winner that you were talking about, Giovanna, but she's not 40. She's about 50. Anyway, so now in China, there is an experiment like this as well. They're all over the world, but no success so far. But I think it's a difficult enterprise, and experimentalists are still working hard on this. So I'm going to take it for granted that that is the dark matter and tell you a little bit more about the consequences of that. So let me summarize where I am so far. So what have I told you so far? I've told you that even though there's billions and billions of galaxies and stars in the universe, normal matter makes only 5% of the universe. 25% is dark matter. The evidence comes from the velocities of stars in galaxies and from this strange gravitational lensing phenomenon. The dark matter is probably an elementary particle not yet discovered. The lion's share of the universe is dark energy, and the evidence is the accelerated expansion of the universe that has been measured. We don't know what it is, probably associated with the vacuum. So that's what I've told you so far. And now I want to ask a simple question, which goes back to the question in the title of this lecture. Why is the dark matter so interesting? Why is it so important? The reason is simple. Without it, we wouldn't be here. So the dark matter, or the gravity of the dark matter, is what drives the formation of galaxies and all cosmic structure. And so let me now tell you where galaxies come from. Now, this is an amazing story, and it really is one that has been developed over the last 40 years. And I regard myself as immensely fortunate that I was a scientist just when these ideas were being developed, because they're pretty astonishing. The story begins very soon after the Big Bang. In fact, it begins when the universe was a mere 10 to the minus 35 seconds old. That's a decimal point, 34 zeros and a 1. At that time, something very strange happened. The universe, oh yes, and I'm going to tell you about nothing. I'm going to tell you about the vacuum. So the universe, when it was born, it was trapped in a very strange state, which physicists refer to as a false vacuum. It was a state that was anomalous. There was too much energy for the universe to proceed in its evolution. So the universe decided to shake off this extra energy by expanding exponentially fast during a very short period of time known as cosmic inflation. Now, this energy is related to quantum phenomena, the phenomena that describe the physics of atoms, the quantum physics. And any of you who has come across ideas in quantum physics knows that the quantum world is a world where everything is fluctuating, everything is changing in so-called quantum fluctuations. So here's my attempt to make a movie of quantum fluctuations. So in the vacuum, there are continuously these quantum processes in action that manifest themselves as, don't be scared about this, but matter and antimatter spontaneously emerge out of nothing, and then matter and antimatter annihilate into energy, which then in turn decays into matter and antimatter. This is going on and on all the time in the vacuum, and these are called quantum fluctuations. And the proposition of modern cosmology is that the quantum fluctuations associated with inflation are the origin of everything we see in the universe. Those of you who are not physicists, this is the hardest part of this lecture. And if you don't know about quantum physics, all you need to know is that everything changes. It's called the Heisenberg uncertainty principle. In physics, everything fluctuates, and this phenomenon of inflation produce small inhomogeneities in the early universe of quantum origin, which evolved to make the galaxies and all the other structures that we see around us. And I'm going to tell you a lot more about that in a minute. Dark matter was produced, as we said, a little bit later, and the gravity of the dark matter is what amplifies these small fluctuations. So galaxies originate, according to modern ideas, from tiny quantum irregularities amplified by the gravity of the dark matter. So now, what I just told you, I went very fast, so you would maybe register, but I just told you something absolutely absurd. Everybody here, our galaxy, our sun, we come out of quantum fluctuations very early on in the universe. So if Einstein or Newton walked through that door, what would they say? Well, I know exactly what Einstein would say. This is what he would say. And I know what Newton would say. He would say, I'd rather be a musician. So that's why Newton's reincarnation is a musician. However, they would agree with me that modern science has one overriding principle. For it to be physics, any proposition, it has to be testable. So physics is great. You can come up and with any crazy idea you want. So long as your idea is testable, you get paid at the end of the month. You're doing physics. If your idea is not testable, you're doing something else. And so these ideas are testable. They are physics. How do we test them? So now let me tell you how we test them. Turns out that the early universe was very hot. It's called the hot Big Bang. Not surprisingly, because all the matter in the universe was compressed in a state of very high density and very high temperature. Now, as the universe has expanded, this radiation has cooled down. And about 350,000 years after the Big Bang, there was an important moment in the history of the universe because that's when the first atoms of hydrogen formed. Now, hydrogen is made of protons and electrons. Before this time, the universe was too hot, so the electrons were just floating around, and they are like a fog. They interact with light, and they stop light from propagating. But when the first hydrogen atoms formed, then the electrons went into atoms, and the light was free to escape from the Big Bang. And that light is the first light of the universe, and is light that has been propagating for 13.4 billion years. But that's, I've talked about 350,000 years. So that is the human equivalent of 1 day. When this light was emitted, the human equivalent of 1 day old. That light has been propagating to the universe, and because the universe is so old, and this radiation cools, today it has cooled down to a mere 2.7 degrees above absolute zero. So this is very, very low temperature radiation, and low temperature radiation appears in the form of microwaves, and so this radiation has cooled down to microwave wavelengths, and it was discovered in 1964 by these two American engineers, Arnold Penzias and Bob Wilson, who accidentally came across the discovery of the heat left over from the Big Bang. They weren't looking for it. They didn't even know it existed. They had built a radio horn trying to do radio astronomy of the sun, and they were very annoyed that when they were trying to calibrate their instrument, wherever they pointed it, they had this residual noise that three people in Princeton, one of whose picture you will see in a minute, explained to them, this is the heat left over from the Big Bang. So Penzias and Wilson had discovered entirely accidentally the Big Bang. And of course, they got the Nobel Prize for that. Now, so that is known as the cosmic microwave background radiation. And it's wonderful. It's radiation left over from the Big Bang that brings us news about the conditions that prevailed when the universe was the equivalent of a human equivalent of 1 day old. So by studying this radiation, we can tell what was going on in the universe at this very early time. So what was going on is we had these quantum fluctuations. Gravity amplified them, made them slightly bigger. They're still very small. But when the radiation is emitted, we can investigate these small, tiny ripples or irregularities. In this case, irregularities in the temperature of this radiation. So in the 1980s, colleagues predicted what the temperature of this radiation should look like, and it should make a pattern like this of hot and cold spots reflecting these quantum fluctuations. So as you look across the sky and measure the temperature, then you should find that it's not the same temperature. It should differ from one point to the other by a very small amount. The differences between the hot and cold spots are only of order 1 in 100,000. In 1992, April 22nd, to be precise, was a very important day in science. The COBE team, it's a NASA satellite, published this picture. And what you're looking at here is the temperature of the heat left over from the Big Bang. It's all around us, but in order to put it on a picture, projected in this way. And what you see here is that the temperature is not constant. It has hot and cold spots. And this was, say, a turning point in the history of modern science. It made the front page of newspapers across the world, like this one. And so I hope you forgive me. I'm going to leave modesty aside. I did play a role in this, which was reported in The Independent, and those sitting in the front may be able to see. Carlos Frank, an astronomer at Durham University, said yesterday, "Oh, wow, you have no idea how exciting this is." So this is my great contribution to cosmology and my great contribution to science. And my wife knows that when I die, my epitaph will be, "Oh, wow." Now, of course, this discovery earned my good friend George Smoot the Nobel Prize in 2006. This has been remeasured with greater resolution by 10 years later by the WMAP satellite, and then 10 years later by the European Planck satellite. And the Italian physicists played a key role in Planck. In fact, I was part of the Italian team originally, but I decided space science was too difficult, and I pulled out of it. But this is a great contribution of Italian. It's an international European Space Agency mission. The French played a key role, the British, the Americans, but the Italians were central to the discovery of, well, to the measurements of Planck. Now here's the only technical plot I have, but the details don't matter. So what's plotted here is just something to do with the temperature, with this pattern. It's a mathematical description of this pattern of hot and cold spots. For those of you who are physicists, this is just the power spectrum of the temperature difference between 2 points as a function of how separated the points are. It doesn't matter. The details don't matter. All I want you to understand is that these predictions are complicated. They're not trivial. They have wiggles. They were made by Jim Peebles in 1982. The Planck measurements in 2003 look like that. So plotted here are the theoretical predictions from Peebles in green, and in red are the measurements of the Planck satellite. Now, I've seen this picture thousands of times, and I always have difficulty not breaking down in tears or something because it's so incredible. So what you see here is one of the great wonders of the human mind. So firstly, you have to ask yourselves, why is it that in this corner of the universe, a species of animal has evolved capable, on the one hand, to make predictions about how the universe began, the green line, capable of developing the language of mathematics upon which this is based. That's the green line. And the same species of creature has also evolved to have the ability to construct machines that they launch out of their planet, capable of making measurements of accuracy 1 in 100,000, because that's the amplitude of these signals. So that, to me, is absolutely remarkable. And the agreement between the theory and the observations is the evidence I was promising to you, the evidence that there was inflation, because these predictions are based on that theory of cosmic inflation, quantum fluctuations, and cold dark matter. And here, I want to pause for a second and show you a picture of the great cosmologist. He really is the greatest of his generation. He's 80 years old now, Jim Peebles. When I was telling you about the three people who explained to Penzias and Wilson what they had discovered, one of them was him. He was a PhD student in Princeton at the time, and he finally got the Nobel Prize in Physics in 2009. He is the mentor of my generation of cosmologists, and we all look up to Jim as one of the great scientists of the 20th and the beginning of the 21st century. In fact, we've already mentioned today the two I think are the greatest, Jim and Martin Rees, that we talked about earlier with the rector. Anyway, so to me, that picture is the scientific equivalent. It's a great accomplishment of human civilization, the scientific equivalent of a Rembrandt picture, of a Beethoven symphony, but in many ways better than that, because Rembrandt was one individual genius, so was Beethoven. This is the work of thousands of physicists and engineers over many, many decades. Right, so I'm nearly done. So here are these quantum fluctuations from inflation, which are the precursors of galaxies. And you might be wondering, well, all too good, but how do we know these evolved into the galaxies? And just want to show you how we know that. And we know that, again, through the use of the laws of physics. So these conditions here provide the initial conditions for the universe. And all we need to do now is apply known laws of physics to work out how these small perturbations grow to produce galaxies. And we do that using computers, because the universe is very big. In particular, a new way of doing science that has emerged over the last 30 or 40 years called computer simulations of the universe, which is what we do at my institute. And other people here, a colleague of mine from Santa Cruz, he does that too. Piero Madao sitting over there. Michele Fumagalli also does this. And of course, Alejandro Benitez Lambay, who's sitting over there, is one of the world experts on the subject. So what we do is we make some assumption about the content of the universe, 70% dark energy, et cetera, et cetera. And then we just solve the equations that we know and love from physics. They look slightly impressive, but these are very well established, that 19th century and 20th century equations that we know how to solve. They're not that easy to solve, so we rely on a computer to help us. And computers are great because in a way better than PhD students, because they work on weekends and they never make mistakes. And the one thing they don't do, which students do, is they never answer back. And to me, the important thing for students is to answer back and not take the word of the professors as the truth, but to question what it is. But the computers don't do that. They just do what you tell them. You go away and see what comes out of the computer. So to finish off, show you some of the things computers can do. So here is, I'm going to show you a movie from a calculation, from a supercomputer simulation of how the clump of dark matter of a galaxy like the Milky Way comes about. So this is a very early time. These are the quantum fluctuations that I was telling you about before, amplified by gravity already, but it's very uniform. So these small irregularities is what I've been telling you about before. And now we're going to let the force of gravity act on those small irregularities. And what you can see they do is that they begin to concentrate matter because gravity attracts. So wherever there was a slight overdensity, matter floats towards it. And then soon lumps begin to appear. And they make these amazingly beautiful structures called the cosmic web, characterized by these filaments. And well, it's better without the lights. And here you see gravity in action. Here's this lump being attracted by, well, actually, sorry, it went past it, but it's going to come back because the movie is rotating. But anyway, these clumps are attracting one another. I think this is the one I was thinking about. So these clumps are going to flow here because of gravitational attraction. There you see the one one's eating up that one, and then is merging with that one. That's just gravity, bringing them together and building larger and larger structures from this beautiful cosmic web. So that is how we think the halo of galaxies like the Milky Way formed. The universe here is still quite young. The simulation goes up to the present day. It's only 2 billion years old, but nothing much happens in the remaining 10 billion years. So let me move on to another very famous picture called the Millennium Simulation. You can download it from the web. If you look for something called the Virgo Consortium, then you'll find this movie. This is a fly-through the universe, and what you would see if A, you were able to see the dark matter, which of course we can't, and B, you were able to travel much faster than the speed of light. So you would see this amazing richness of structure, all of which, this present day distribution, all of which emerge from these quantum fluctuations of inflation. So the universe goes from being very, very smooth, very, very simple, to being very well structured in this complex and, if you allow me to say so, beautiful way. Now, in the last 10 years or so, there's been a breakthrough in cosmological simulations in that I spent most of my career simulating dark matter, but now we're able to simulate not just the dark matter, but also the ordinary matter, the 5%, which is, of course, responsible for the galaxies and the stars that we see around us. So several collaborations across the world. We have another world expert in the audience here, Andrea Macho, sitting over there, do these sort of calculations as we do them in my institute, where we're now trying to understand in detail how galaxies like the Milky Way came to be. So here's a movie from a collaboration called the Eagle collaboration, based in Durham and Leiden in the Netherlands. And you will see now the formation, not just of dark matter clumps, but of actual galaxies. So here's dark matter, but now we cut to the gas, mostly hydrogen and helium left over from the Big Bang. You see the dark matter is behind it. You don't see it, but it's causing these lumps to be attracted to one another. Things begin to spin in ways we understand from simple physics. And the gas can dissipate energy, so it settles into spinning disks that you can see there. Now we cut to stars. The simulation includes prescriptions for turning gas into stars. And then you see how this object grows as it attracts through gravity other lumps of gas, which then also give rise to the production of stars. So, and this, we're focusing on one galaxy, and in a minute, we're going to zoom out and see that this kind of thing is happening all over the universe. Here's the stars coming up in blue. And this movie was made by a former student of mine, Rob Crane, and a colleague of mine, Richard Bauer, at Durham. And here you cut back and you see this activity going on throughout the universe. So let me show you some images of galaxies. Now, I don't know if there are any amateur astronomers here. You might think that these images come from the Hubble Atlas of Galaxies. No, they don't. They come from my computer. They come from a cosmological simulation. And this is what we're capable of doing today. I reiterate, just using the laws of physics, we are able in the laboratory to make galaxies that for all intents and purposes look just like the real thing. So let me conclude this lecture this morning. I told you a story that begins very soon after the Big Bang, 10 to the minus 35 seconds, when the universe went through a period of cosmic inflation. Cosmic inflation seeded the universe with these quantum fluctuations that eventually we see reflected in the temperature structure of the microwave background and as a pattern of hot and cold spots. And recent measurements by the Planck satellite agree perfectly with the theory that was put forward 30 years earlier. And it is this, through the power of computers, we can calculate the consequences of these processes and produce galaxies in computers. These are real galaxies, by the way. These don't come out of my computer. From these quantum fluctuations of inflation. So let me just finish off with one of my favorite pictures, a triptych, The Garden of Early Delights by Hieronymus Bosch. It has three parts, like triptychs tend to do. This is Earth, this is Hell, and this is Paradise. So here on Earth, I put a question that's still open. What is the dark matter? I think that's an earthly question. It's an experimental physics question. It's one that I'm sure will be solved very soon, in the next 5 years. Mind you, I've been saying that for the last 20, but I think this time I'm serious. I think we're very close to discovering the dark matter. So that's an earthly endeavor. Here in Hell, I put the dark energy because we really know nothing much of substance about dark energy. I don't think my generation will solve the problem. Maybe Michele's and Alejandro's and Mateo, wherever he is here, they might solve it. I don't know. It is a hellish problem. But here, for Paradise, I left perhaps the most profound question of all. How did the universe begin? So we know, of course, as I've been telling you, that there was a Big Bang. But as Martin Rees says, we don't know what went bang. And so that, I think, is a heavenly question. Whoever answers that one, I'm sure will proceed to paradise. Now, so these are open questions for new generations of physicists and scientists, and humanity, for the reasons that we discussed earlier with Giovanna. The society has decided to invest serious amounts of money in trying to answer these questions. There are facilities and telescopes all over the world. Italy plays a major role in many of these. In many of these new generation of telescopes is the James Webb Space Telescope. Watch out, it's going to put out its first images very soon, in the next couple of weeks or so. So watch out for that. But in addition to these expensive facilities, we have the power of the human mind, and greatly enhanced by the power of computers. In fact, the most powerful computers, like the one in my university, is already capable of doing more operations than the human brain. So the future there is pretty unlimited. So let me leave you with an image of my city by telling you that there has been tremendous progress in cosmology over the past 40 years, but I think some of the best is still to come by, I hope, the new generation of scientists, some of whom are represented here today. And I will leave you with that and a picture of my institute. Thank you.
I'm a little ashamed of stealing the microphone from your hands, but I have to. So we have the time for 2 or 3 questions, and then we proceed with the schedule of the day. So don't be shy, and because it's a great occasion for everyone. over there. If you want to come and join us here, okay. So I come to you and I bring the microphone so everyone can hear you.
Just a curiosity, actually. I was wondering, okay, hi. I was wondering, how likely is it for you that dark matter just doesn't exist and Einstein's general relativity is just like wrong?
It's an excellent question. So so the question is, what if instead of having dark matter to explain these phenomena, the ideas about gravity are incorrect? So there's two answers I can give about that. So I think and there are a few, not many physicists who work on alternative theories, particularly something called MOND, Modified Newtonian Dynamics. Is there anybody here who works on MOND, or can I be rude? So I think the evidence for dark matter, in my mind, is pretty compelling, particularly gravitational lensing. And MOND doesn't really have a way to explain. MOND is this idea whereby Newton's law gets modified in order to account for the speed of stars around the Milky Way. So it can do that by changing Newtonian physics, which is part of relativity in a way, but it cannot explain many other phenomena, in particular gravitational lensing, in any simple way. So I think, I don't think MOND is the answer. I think there's only a handful of people who work on that in the world. And once they die off, then I think MOND will go with them. But there's another side to your question. And that is, in fact, and that is I think in my mind, has a lot more promise. Could relativity be wrong? And could the dark energy arise from some correction to general relativity? Now that is also called modified gravity, but that is a perfectly, I think, in my mind, rational way to try and explain the accelerated expansion of the universe. At the moment, we just don't know. We have something, I didn't talk about it because of lack of time. The standard picture of cosmology assumes something called lambda, which is a cosmological constant, that actually Einstein was the first to talk about it for the wrong reasons. But that's almost certainly too simplistic a view. So I think there's a lot of room for what you say. And it may well be that gravity needs to be modified, but not to explain the dark matter, but to explain the dark energy. And I think there's many people across the world trying to see whether they can understand the accelerated expansion of the universe by introducing small modifications to Einstein's theory of relativity. So that, I think, it's a perfectly, rational and intelligent thing to do. MOND, I just think the more I look at it, I mean, I have written papers on MOND. The more I look at it, the more flaky it looks to me. By that, I mean, it's not, so I don't think, so I have a philosophical problem with that. If you have a problem in nature, and, and it doesn't conform to what your expectations are, but you should try to use the toolkit you have, the laws of physics, to see how you can make sense of that, rather than go and change your toolkit. You know, so if your car breaks down, and you have some tools, well, try to fix it with the tools you have. Don't throw your car away and all it had was a puncture. Or so that's why I don't like, another reason I don't like MOND. I don't think that's the way we should do science. You shouldn't give up on the edifice of physics just because the stars seem to be rotating too quickly. We just have some dark matter. And then we have independent evidence of the dark matter through lensing. So that's my answer to your question. But I think it's a very, very interesting and profound question. But I think particularly in connection with the dark energy.
Another question?
So, Carlos, you made the bet that in 5 years we'll understand the nature of the dark matter particle. Now, there are experiments that are trying to find out evidence of inflation from gravitational waves, etc. So what's your bet? Will we find strong constraints on inflation based on those experiments over the next years?
Oh, that's a very interesting question. He's a professional. He's Professor Piero Madao from the University of Santa Cruz. He's Italian, as you can tell, and he's a very old friend of mine. Now, that's a very good question. Now, I should make a confession that I've already lost one bet. I bet that dark matter would be discovered before gravitational waves, and I'm not convinced I lost. I tell you why, but it appears that I lost because, as you may have heard, gravitational waves were discovered 6 or 7 years ago. These are there are perturbations in the geometry of space-time when black holes collide. It was a wonderful discovery, got a Nobel Prize as well, and it was discovered before the dark matter. However, the dark matter may have already been discovered. There are experiments that I didn't explain here, and I don't have time to go into the technical details, but that might have already detected dark matter, but the community is extremely skeptical. I think science is just organized skepticism. So there are no nastier people than scientists. So you have to be, you want to be a scientist, you really have to have the ability to take criticism, because that's why science is so wonderful and so powerful. New ideas are not welcome with open arms. They're always faced with criticism, and then you have to surmount the criticism. So there may be that the dark matter has been discovered, but there's no consensus about that. Now, what Pierre is asking is even more profound than dark matter, and that is inflation could have left a signature, because inflation caused the universe to shake. Because of this quantum phenomena, the universe started shaking, and this shaking of this very dense state of the universe would produce gravitational waves. And in fact, Planck, that I talked about, looked for this evidence for these so-called primordial gravitational waves, hasn't found them because they're probably below the detection limit. And there are many experiments all over the world, particularly in the United States, trying to discover these primordial gravitational waves from inflation. The technical word is B-mode polarization, so look out for that in the newspapers. But there are experiments that might, in fact, detect these gravitational waves. Now, Piero is asking me to bet again, so I'll make a bet with Piero here in public. I don't like to bet much, but I will, that dark matter will be discovered before before gravitational waves from inflation. So it's 100 euros on that, Piero. And we have the rector as witness. That's not the way you do science.
Okay, we will cut this part. Thank you. And maybe the last question. Otherwise, I have a super quick final question. Okay.
Hi, and this is only a curiosity. You showed us the plot which showed the perfect, almost a match between the theoretical predictions and the measurements of the CMB anisotropies. And you said that that could be considered as an indirect proof of the inflation theory. Since I've heard about, I'm not an expert at all, I've heard about a new kind of models such the cyclic model by Steinhardt and Turok. And can these alternative models justify in the same way that inflation model does the anisotropy spectra, or doesn't them?
Well, that's a great question. Thank you so much for that question, because it allows me to make a point. So what he's saying, and you must be a physicist since you use the word anisotropy. So the picture that I told you about today of inflation, particularly, is not the only way to explain that Beethoven-Rembrandt picture that I show you. Now, after that was published, there have been other theories by a few people. Neil Turok is also a very good friend of mine. Paul Steinhardt not so much, but Neil, well, anyway, but so these are very, 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 very good physicists, as are the Mond people, by the way. Bekenstein, who's the originator of Mond, is also really, really distinguished people. So, and Roger Penrose is another person who has put forward ideas of cyclical universes, because one thing these people don't like is the fact that if the standard model, as we call it, of cosmology is the correct description, then nobody asked me about this, but I'll tell you, the fate of the universe is not very encouraging, because the universe will continue to expand forever. And in fact, it's already expanding faster than the speed of light. And the result of that is that as the universe grows old, more and more of the universe expands faster than the speed of light. That is allowed by relativity, by the way, because there's no information exchanged. And so eventually, what we call our horizon will shrink. We won't be able to see very far. In fact, eventually we won't be able to see outside our own galaxy or our own solar system. But so the future, it looks grim. And particularly some people have difficulty philosophically with living in a universe that is going to be around forever and in a very uncomfortable state. I mean, I could tell you all sorts of horrible things that will happen in the future, but so they would like some form of rejuvenation. And in the old days, we used to talk about cyclical universes that would expand and then reach a maximum size and then collapse and maybe produce a new Big Bang. And so that was much more philosophically reassuring, because we don't face this very grim future. Now, Neil Turok, Paul Steinhardt, Roger Penrose, who also got the Nobel Prize for black holes, they are very keen on this idea, put forward some very interesting suggestions. So now, but the difference is this between what they're telling us and what I told you today. And the difference is the following. I showed you predictions that were made 30 years before the experiment. And that's the way science, in my mind, works. You make a prediction for a new phenomenon, then you decide an experiment to test it. These other ideas have come after the fact. So they didn't predict anything. They accommodated observations, measurements that were already there. Now, that's fine. They may be right, but I would really like, and I keep saying this to Neil, them to make predictions for new things that have not been discovered. Now, Neil Turok, not Steinhardt, but Turok, has a new model where he does make predictions, in fact, interestingly, about the nature of the dark matter, and that's testable. So if I come again in a few years' time and Neil's ideas have been, predictions have been vindicated, then that's the way science works. We will replace our standard model by a new way of thinking. But I think the beauty of what I told you today is that the theory came before the experiment and is not retrofitting anything. It is actually an ab initio development. So, and that I think illustrates the power of science. Doesn't mean to say, I'm sure it's not the last word, certainly. So, but yes, and right, and what I do like about these ideas, I too feel uncomfortable in a universe that's going to expand forever, where the horizons are going to shrink. So, and that's why this subject is so wonderful. And that's why there's so many open questions for young scientists here to pursue. And maybe they will tell us some of the answers that we don't have today.
Thank you again, Professor Carlos Frank, and of course, Rector Giovanna Iannantuoni. And thank you for your great attention and passion to be here today with us. Let's proceed with the schedule of the day, and I don't know, Maria or other Bicocca staff can lead the day. So thank you. Thank you.